this computer. Okay, hi everyone who's watching on record. Welcome to Python Club. Today we're going to do part 5 of Back to Basics. So if you don't already have the link is available in the Slack, or alternatively it's on our GitHub in, here it is. Okay, so the Back to Basics solid notebook has a link to, I should bring up this notebook, which has a link at the top to the Colab version. So that's how to find us here. So let me figure out where we're at. So we've been going through a few things to do with a particular protein or a particular enzyme. We had a little look at its sequence, and then more recently we downloaded its structure and then worked on extracting the coordinates, the 3D coordinates of all of the atoms in the structure into a pandas data frame. And then I think in the last lesson we were working on the distance in the 3D space between each atom. Yeah, here we go. Okay, so we used Euclidean distance, which is just Pythagoras in 3D, to calculate the distances between each atom. And then we had a look at how difficult it might be to execute a pairwise distance measurement for every atom against every other atom in this set of about 8,000 atoms, which results in quite a lot of computation. So we did a small experiment to sort of gauge how the time taken to compute the calculation sort of increases as you add atoms, and it increases exponentially. So at a certain point, it becomes very worth it to find shortcut. And our shortcut came to us in the form of an algorithm within SciPy, which is a scientific computing library. And our algorithm in particular was under the spatial algorithms subsection of it, and it was called KD trees, which is a method of dividing up 3 or more dimensional space into a series of smaller chunks, and then grouping each point, in this case atoms, by chunks where they are in space, which means that then you can say I only want distances that are less than 10 angstroms anyway, angstroms being the distance unit we're working with here. Then we can cut down on the number of calculations we have to do, because we can just do the calculations with atoms that we already know are closer together. So we did exactly that. We imported the KD tree class from SciPy Spatial, and we initialized it around a coords object, which was, I think, a NumPy array that contains the XYZ coordinates of all of the atoms in our protein. We looked a little bit about getting help, and I think we got as far as making a sparse matrix. So to re-explain, a sparse matrix is a matrix of numbers where there's an abundance of a repeated value. So in this case, there's an abundance of zeros, and our matrix is just over 8,000 by 8,000, so that's potentially quite a lot of zeros. So the idea behind a sparse matrix is that it doesn't bother storing the abundant repeated value, because you know it's just going to be 0 every time, in this case at least. So instead, what we do is we store a lookup to anything that's not 0 and just store that, and you can end up storing, like, you know, maybe about 1% of the data that you would otherwise be storing. So in this case, we created an object called dist, which is short for distance. And sorry, I've scrolled up. Okay, so our KD tree, which we assign the name KD, has its own method associated with it called sparse distance matrix. I never quite got to the bottom of why you have to feed it this method itself as an argument, but sure. And what this function does is finds all distances that are less than 10 angstroms away from each other. And because I'm doing it via the KD tree that I mentioned earlier, it means that the computation is actually much more efficient because it just doesn't bother with anything that might be above 10. So it returns this object called a sparse matrix, like I mentioned before. And there's a few functions and methods in that to be aware of these sparse matrices. You know, like I said before, they're mostly zeros. You can do some simple methods, like for example, count all of the non-zero elements, which in this case comes to just over, what's that? Just over 1.2 million. Okay. Similar to a NumPy array, we can get the shape out, which is, well, it's a square matrix, so just over 8,000 by 8,000. And to look at the fraction of non-zero values that we're dealing with in this matrix, we can calculate the number of non-zero items and divide that by the total number of items in the array, and that is the shape, 8,000 and something, times 8,000 and something. So that's the raw fraction, which pretty much comes to 1.6%. So if only 1.6% of our values in our pretty big matrix are actually numbers, then it does make sense when you get to this scale to actually start dealing with these numbers in a sparse matrix. Not only can it save you computation time if you implement special ways of doing, say, multiplication in that, it also saves your RAM, which if you're working with, say you're working on a laptop with not very much, then you could crash your computer if you don't handle your memory properly. Okay. We have a few other methods associated with these sparse matrices. So for example, we can find the coordinates of all of the non-zero items. So this returns you a tuple of two arrays, a tuple being similar to a list, but in curly parentheses, containing one or more items as a collection. So it returns us an array with x coordinate and y coordinate, or sorry, the row coordinate, then the column coordinate, I should have said. And then to get the values that are associated with that, we can, similar to how you would with a dictionary, you can call a function values, and then we get the items that correspond to each of those coordinates. Yeah, there are a couple of formats of sparse matrices, and the one that we've ended up with here is called a dictionary of keys matrix. But other formats include the coordinate format matrix, which similarly contains, rather than the dictionary of the column and row coordinates and then the values, it similarly just contains coordinates. There's a few others to be aware of, but they're fairly easy to interconvert between each other. I think if you want to find out more about that, then just refer to the SciPy documentation as you go. To look up a particular value, you can do exactly as you would, or similar to how you would in NumPy, using slice notation. Although in this case, because we're dealing with a dictionary type sparse array, I've opted for using this tuple as a key. Are there other ways of doing that? Not sure. Let's carry on though. Indexing in sparse matrices. So similar to a NumPy matrix, we can take slices of our matrix with this slice notation here. So we'll have the rows 0 to 5 and then the columns 0 to 5. And we can slice just like that. We can also do rule-based slicing so that we can, extract numbers greater than or less than such and such a value, or apply a function that checks if the value inside meets a criteria or something like that. So although they're different to a normal matrix, they are as useful. There's just a different format to be aware of. Another useful function associated with these sparse matrices is the method toDense or .toArray, which, as the name suggests, turns it either to a dense matrix or to a NumPy array, which differ slightly in how they behave. I think for more predictable behavior, perhaps go for toArray. That leads to a standard NumPy array. And you can see it returns here the actual values of the top left corner of our matrix. We can see along the diagonal, it's all zeros, as you'd expect, because these pairwise distances, along the diagonal, that's where it corresponds to itself, and its distance to itself is 0, so that makes sense. Okay, and that leads us on to exercise 5.1. What did I write here? Okay, yeah, so down here, I called the toArray function on our distance matrix that we defined in one of the cells above. And I also called the .flatten method on it, which, as you can imagine, will turn our 2D matrix into a 1D matrix. And I did that so that the histogram wouldn't treat different rows as different categories. I just wanted to sort of lump them all together. So that's why I opted for flatten there. And what we see here is mostly zeros for our whole distance matrix. There's 10 to the power 7 zeros up here. And we can't really see any of the non-zero values. So your exercise here is to create yourself a code cell and plot a histogram of the non-zero values. So non-zero values, you'll need to, I'm wondering if I left you enough clues in here to, yeah, okay, I think I have left you enough clues. So yeah, your tasks then will be, extract the non-zero values from this object dist, and then plot it as a histogram, and then add any aesthetic changes that you might like. If anyone has any questions, then let me know or put it in the chat. Let me bring that up. And I will start a timer for 3 minutes. 3 minutes for now, and then we'll see how it goes. Okay. Okay, how did it go? Did anyone have any problems with that exercise? Okay, let me find my notebook. Right. So, our task was to plot a histogram of all of the non-zero values. So we can break down that task into number one, find the non-zero values in our object dist. So in this text section above, there was a line that we can lift out of it called dot values, which, like I briefly mentioned earlier, extracts all of the non-zero values within that sparse matrix. There we go. And then from that, we can build our histogram around it. So I'll wait to see what this output gives us. Or will I? Whilst I'm waiting, I'm just going to start putting in the code for a histogram, plt.hist. And let's see what happens if I paste in dist.values into it. plt.show to have it render. There we go. Okay, so it's worked, and it seems like I didn't have to flatten the matrix like I did before, although we can have a look at what shape this matrix is. Has no attribute shape. Okay, I'll take that back. I guess we can't. Okay, so we can see that all of our distances marked on the x-axis are less than 10 angstroms, which is good. And we've got the default number of bins in our histogram, 20, which is fine for most applications, but for this one in particular, we're losing some information because we have so many data points that grouping them together quite coarsely, as you can imagine, we'll miss some stuff. So I'm going to set the number of bins to 100 for a finer resolution. And look at that, you can see two major spikes of distances in the small distance section. So for the purposes of this exercise, what we're going to say is all of the bond lengths between 1 and 2, we're going to say are covalent bonds, and everything between 2 and 3, we're going to say are non-covalent bonds for the purpose of this exercise. Although, if anyone knows anything about this peak here, which may correspond to more non-covalent bonds, then let me know, and then maybe we can set our maximum bond length to 4 or 5 or something like that. If you were wanting to add aesthetic changes to the graph, then plt.xlabel would have been a good one to do. Distance in angstroms. That's the unit that we're dealing with here. There we go. And for now, we'll skip out titles and so on. Okay. So for this section, now we want to separate out all of the bonds that fit into either of our two proposed categories. The 1 to 2 angstrom short bonds and the 2 to 3 angstrom long bonds is what I'm calling them at the moment. So one way to locate values in a sparse array is by simply using a size comparison. So for example, in this cell, I take the top left corner of the distance matrix, and then I ask it to return either true or false based on whether or not the number in that cell is less than 2. So as you'd expect, along the diagonal, being all zeros, yeah, there we go. Being all zeros on the diagonal, all of them return true because, of course, they're all less than 2. And there's a few falses here and there. But for our task, we want to find numbers within a range, numbers between two numbers. And at that point, it gets a little more difficult to put in these greater than or less than operators. So I found a sort of, well, we can call it a hack from Stack Overflow, which if you haven't come across Stack Overflow already, it's a web forum where people will post in code issues, and normally there are some good answers from just community members. And it's normally one of the first ports of call for debugging code. So I found this solution to sort of multi-level filtering in these arrays, and the solution is to multiply your original matrix by a second true or false matrix, a Boolean matrix. And in that case, the way that is handled under the hood is that falses are treated as zeros and trues are treated as ones. So for every cell where your case is false, then you'll just get a zero in the resulting matrix. So what do we have here? Our top left corner, and then we multiply it by another array that is this array, but only values that are less than 2. So it achieves the same as above, except number one, it doesn't get rid of the values in the cells, which leads on to number two. Not getting rid of those values lets you then put another multiply statement onto the end, so that you can have a second set of criteria of true, false, or 1, 0 statements to give you another level of filtering. So below in here, we have our top left corner up to 5 and 5, and we multiply by all of the cases where the answer is less than 2, and then where the number is greater than 1. And then at the very end, I call .toArray to make it readable for us. And yeah, we can see here that we found all of the items between 1 and 2 angstroms. So your exercise here is to follow on from that and create an object that represents all bonds in our protein that are between 1 and 2 angstroms, and then create a second matrix that contains all bonds between 2 and 3 angstroms for now. There's no need to call them as a dense object just yet, but if you want to play with that, then go right ahead. I will start your time in just a second. And then after this exercise, we'll see how we can use these short and long bond representations to create a new data structure that lets us do some more interesting analysis on our protein. Okay, I'm going to give you 5 minutes. Off you go. How's everyone getting along with that? So the print screen button on my keyboard is right next to the control, so I press it by accident all the time. Really annoying. I'm going to start the countdown timer now because I'm bored. Sorry. I think I might need to get some unlicensed music to play in the gaps to keep myself occupied. We'll find something next time. Okay, so our tasks were find all of the bonds between 1 and 2 angstroms and then do exactly the same operation for between 2 and 3. So let's give that a go. We were trying to find them from the object dist. And we want to locate dist by everything less than 2. So let's have a look at that. That should return our true-false matrix. Sometimes people call these masks for looking up values. It is taking a while to compute because although it doesn't have to do every single value in the whole 8,000 by 8,000 matrix, we did see earlier that there are about 1 million values for it to look at. So you know what, for the sake of developing this function, I'm just going to do at the top corner. Okay, give me a second of being stumped by my own exercise. So the way that I was intending to do it was with the multiply followed by another multiply. So what I was hoping to show was that the top corner where everything is less than 2 should return a true-false matrix. So let's wrap that in brackets and tell it to array to give an example, a flavor of what that returns. Here we go. So trues, falses, which, like I mentioned earlier, will get treated as 1s or 0s. So this dot multiply. So ignoring then just the top left corner and performing this on the entire distance matrix, we can multiply by a mask where everything is either true or false, depending on whether or not it's greater than 2. And then we can multiply it again by whether or not it is less than 3. Have I got that right? Greater than 2, less than 3. And let's call that short bonds. And we can have a look at the top corner. To array. Let's see what that gives us. So it might take a moment to compute. We're getting a warning that we haven't picked a particularly efficient way of doing this. But it's not a catastrophic warning, so we're just gonna power on through. Okay, so we've located all of the bonds between 2 and 3 angstroms. I've mistakenly called that the short bonds array, so I'm gonna instead go for between 1 and 2. And then I'm gonna repeat the same code for our long bonds. Except this time I want ones that are greater than 2 angstroms and less than 3 angstroms. There we go. Okay, and while that runs, it brings us on to graphs and graph theory. I've left a Wikipedia link dump underneath here. Graphs, I think, are a slightly confusing term for the object that we're talking about, because I think it immediately brings to mind plots. Like, for example, one of the histograms that we made earlier is the sort of thing that it brings to mind. But in the domain of graph theory, it normally refers to a network, is one way of looking at it. So by definition, a graph is a collection of nodes and connecting edges. Like, for example, a chemical where atoms are the nodes and bonds are the edges. The tram line where the stations are the, where the stations are the nodes and the edges are the tram lines, and so on. I'm sure you could think of more examples. But they're a useful data structure as compared to tables for some applications, because they give a notion of proximity in terms of either, spatial proximity in our case, or some sort of relationship with another object. So it's particularly effective at finding relationships between objects. So we're going to look at some graphs that we're going to construct from the distance matrices that we've just built. And we're going to use this package NetworkX, which luckily in Colab is already installed. But if you want to run this on your local machine and you want to install NetworkX there, then as in one of the previous tutorials, use either pip or conda to install it. I didn't drop in as much documentation or links to the NetworkX site as I should have, but I'll add those eventually. But it comes up quite high on Google if you search NetworkX. So in particular, we're going to look at this construct a graph from a sparse matrix. That's what's directly applicable to us. So in this cell, we import NetworkX as the alias NX, which is a fairly standard alias to use for it. And we create a short bonds distance matrix, everything between 1 and 2 angstroms, just like we already did up here. And then we create this graph, G, capital G, using the convert matrix from SciPy sparse matrix. There are several ways to construct a graph, one of which is from a sparse matrix like this. You can construct them from pandas data frames. You can construct them from a dense matrix that has either a 1 or a 0 or anything in between, or any other number that corresponds to 2 items that are linked in one way or another. You can add descriptions for the links. You can add descriptions for the nodes. So it's quite versatile. And then also the package includes various algorithms that are used to work with and analyze graphs, which is what we'll start delving into over the next couple of tutorials. So we create a network X graph from our short bonds object, or at least the top left corner of our short bonds object, which should just contain the first 50 atoms of our protein. And when we have it drawn with default parameters, we can kind of see that it sort of resembles a protein. Our atoms aren't labeled at all, so it's a little bit difficult to make head or tail of it. And also the algorithm used to lay these atoms out isn't aware that we're dealing with a chemical right now. It's just laying them out semi-randomly and trying to keep them spaced. But you can see that throughout there is a single continuous backbone, which is promising because that's what a protein should look like, with every so often a side chain or a dangly oxygen coming out the side. So from that we can take that graphs are a fairly reasonable way of representing both proteins and chemicals. And that brings us on to exercise number 5.3. What are we doing here? Nodes and edges can store additional information like atom identity and bond order, single, double, etc. And we know that the order of atom to atom distances in our dist object, that was the sparse matrix, is the same as that in df data frame. Oh yeah, okay. I remember making this one now. Extract the element symbol for each atom from df and check df.tail. So what do I mean by this? Let's have a look at our df object that we made earlier. So this is our sort of aggregation of various, well, our PDB file. So we have regular atoms, and then towards the bottom we have heteroatoms, which is anything that's not directly part of the protein. So in our case, it includes a lot of water and our heme cofactor, and sorry about that. So what we're after is the element symbol column over here, but the difficulty in this exercise is that the columns haven't quite aligned. So a certain way down, where we should have element symbols, in the het atoms it's switched to being none, and instead having the element symbols, oxygen in this case, in a different column. So what I want from you in this exercise is all of the element symbols, including the element symbols where it should be none and it's just switched over a column, and ideally in the right order. It needs to be in the same order as the atom IDs, so that it lines up with our other object. Okay, and then cell below is the answer. And if you're interested in looking for clues, then you can take a look at our backtobasics.py file, which is here. And the answer is sitting at the bottom in there somewhere. Okay, I'll give us 5 minutes on that, and we'll run through it at the end. I'm going to find a 5-minute song. There we go. Allow me to pick up where I left off. With this phenomenon and a Picasso with a pen. Maybe to restore
bullshit until I hit it with the realness. Figure I should say something, but you don't want to hear me vent. You can talk bad all day long, I will never be impressed. Don't know what I did to make you feel that you be under my respect. You do not scare me, no, you are not a threat. Anyone that want it, they can get it in a flash, no sweat. If you wanna talk on my name, be say with your chest. Got my team on deck, taking out all pawns on my night with a queen in check. Don't get touchy, but we getting the difference. All I do is kill shit, even when I'm chilling. I'm Jay-Z on a bad day, Shakespeare on my worst days. Never been a punk, trust you can get it in the worst way. Fucking let me get a birthday cake in a hate for my birthday. Just wanna switch, then they wanna sit down with bitch. You're not listening, I said it with my chest and I don't care who I offend. Came through swinging at the gate on the mad one, no fox. Stepping to the kid, trying to bring it, I promise you have no love. You sold out for a quick buzz, and honey, you got no love. No less than what I know that I'm worth, and I won't budge. In and out the doorway, shooting through the poor day. And then where would I be now if I went none of your way? I've been exhausted, man, I think I need a tour break. I took a trip to the Philippines, and my Spanish boy hold a hand. Hold on my block, I come back to that. Get out to me more things. Take long on the street, like get anything you want, this is your thing. I follow the white rabbit, got a couple carrots, I know that I got bad habits. Trying to find a balance, I'm in the store like I wanna have it, I gotta have it. You want the toughest or baddest, my pen is the maddest. I probably any caprice, and it's kinda right, I'm at this. Gas said they ain't even on 10, still they can't manage. They think I'm a shy one, like nothing's no flip. They wanna switch, then they wanna sit down with bitch. I said it with my chest and I don't care who I offend. I said it with my chest and I don't care who I offend.
Cool. That was Lil Sims with Offense from an album that she came out with like last year or the year before. Who knows? I suppose that means though that we can't upload this to YouTube when it comes down to it, or maybe we'll have to like mute that section or something. Who knows? All right, I'm gonna start the countdown clock timer anyway because to fill some time. Okay, so that exercise is potentially a bit of a difficult one. I think it represents some of the edge cases that you might come across when you're working with pandas. That is, when data just isn't clean or when stuff just doesn't go right. And I say edge cases; these things actually happen quite a lot. Thanks, timer. Cool. Okay. So if you wanted clues, then the last function in the back to basics.py file in our GitHub tutorials contains the answer, which maybe I'll refer to. I'll try and freehand it, but let's give this a go. Okay, so we have our object data frame, and our problem is we want the element symbol, except all the element symbols aren't all in the element symbol column, which is annoying. Okay, well, for the first lot, we're going to break it down into batches. So we'll go df element symbol and locate just that. And And to get rid of all of these none values, which aren't much use to us, we're going to try .dropNA, which is short for drop NA or drop null values, which in this case also applies to none values. Okay, I'll comment that out for the moment. We'll come back to that. So that will be the main part of our data frame. But we also want to locate the section of the data frame where or the inverse lookup of that. So there's a function called isNA, and it returns false, 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 true, 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 and so on and so on. So we can use this Boolean indexer to index df by exactly that, df.lock. And we'll wrap that in square brackets. And there we go. Now we have all of the data frame for which element symbol is none. And I'm going to take a gamble on that the temperature factor column, which I can either put in here as a separate indexer on the end, or within the initial indexer. So I'm wondering if this does only contain sort of atom symbols. So I'm going to call unique on it, spelled correctly. And we can see that all the unique values are copies of either oxygen, nitrogen, carbon, or Fe, which is iron. So that looks good to me. So the other thing I want to do before I stitch one onto the end of the other is to make sure that the index here is definitely the ID. So I think in an earlier tutorial I did specify that the index should be the ID, which is sort of indicated by the fact that this is an ID. Okay, so the way I'm going to stitch these two items together is, well, it could either be with append or pandas.concat. Let's try both. Okay, let's break down what I've got here. So we've got element symbols where all of the nones are dropped, and to that we have appended the data frame located by where element symbol is none, and then we've switched our column selection to the temperature factor to the left. So let's have a look at that. Okay, looks good to me. There we go. There's our answer to that. So I suppose in terms of the format of the exercise, I didn't explain before what dropNA or isNA is. So apologies for that. Next time I will try harder to make sure that you have all of the relevant information in there. Okay, and then we also have the function imported from the Back to Basics answers file. And very quickly before we finish, yeah, let's do this before we finish. So I mentioned about setting node attributes in NetworkX, and that's exactly what we're going to do now. The attribute that we're going to set is the atom type for each node, or atom in our case, in our NetworkX graph. So I make a short bonds variable that is just like before, a graph that has been built from the sparse matrix short bonds. Then in this row, I use the zip function to iterate through two things at once, G short bonds, which is this graph here, and then atom identities, which we have just defined up here. I list through both of them, and then using dictionary-like item assignment, I assign the element field for each node as J, which in this case corresponds to the atom identity. And then to check that we actually have assigned this property to all of our nodes, I print the first 10 of the short bond nodes, and yeah, we have element identifications for this. So next week we'll talk more about graph theory and its applications in this case, and we'll try and do unravel some of the algorithms that we might be able to use. For example, finding the shortest path from here to here, or finding specific features based on an atom and its neighboring atoms, for example, and trying to see if we can extract something meaningful from that. But in the absence of being able to extract something meaningful, at least it's introduction to graphs, which are a fairly important data structure in Python. That is the end of the tutorial for today. Does anyone have any questions, comments, suggestions, etc. before we finish? Thumbs up? Thumbs up? Amazing.
2 thumbs
All right,
up.
2 thumbs up, and a thanks from Carmen. Well, thank you everyone for coming, and a thumbs up from Steve. Brill. And I'll see you all next Friday for more graph theory based protein bits. All right, bye everyone.
Cheerio.
Thank you so much. Bye.
See you, James.
Bye.